cloud.
Yeah.
Okay,
and that
it's
way,
recording now. Sandeep.
Yeah. And then
Uh-huh.
Megan will put it on. Yeah. Thanks.
Excellent. Excellent. Go ahead, Sandeep.
Thank you very much for the invitation. Yeah, this is, sorry for the delay, technical problems. Okay, so let's go to the next slide. Okay, so this talk is basically based on these two recent papers of mine with Gerard Kaplan. Oh, and please feel free to interrupt me whenever you have any comment, question, or anything, if anything is not clear, because like otherwise it feels like I'm just screaming at my computer. Okay, can you go to the next slide, please? Okay, so the main idea of this talk is actually very simple. It's not even a very new idea. The idea is basically how to constrain space of consistent QFTs just from general principles and symmetries. So in recent years, this has gained a lot of momentum, and it received a lot of attention, mainly because of the success of the conformal bootstrap program. But as I said, by no means this is a new idea. This is as old as quantum field theory. And there are many examples of this main idea. Next slide. My favorite example is basically this bound on massless high spin particles. So if I just give you quantum mechanics and special relativity, and I ask you to combine them, that gives us something rather remarkable. It tells us the menu of massless particle is a short one. Massless particles can only have spin 0, half, 1, 3 halves, and 2. That's it. Not only that, it says actually, it tells you a lot more. For example, it tells you that as you increase the spin, the system gets more and more constraining. For example, you can have as many massless scalars as you like, but you can only have a single spin 2 massless particle, which is also known as the graviton. Not only that, like the interaction of graviton, the soft interaction of graviton to other particles, that's also fixed from symmetry. So basically, a lot can be derived just studying from quantum mechanics and special relativity. Next slide. Naively, one might think that this will also rule out massive high spin particles, because like if I'm performing some experiment at very high energy, all massive particles will appear to be approximately massless. But obviously this is not true, because there is a discrete difference between massive and massless particles. So for example, in 4D, if I give you a particle of spin j, and if it's massless, it only has 2 degrees of freedom. And if it's massive, it has 2j plus 1 degrees of freedom. So there is a discrete difference. So there is, because of that, the argument about massless high spin particles will not apply to massive high spin particles.
Yeah,
so
but it's what you said. It's applied to the spin, say not higher spin but lower spin as well. So it's true for spin starting from spin 1.
What's true?
The difference you are talking about starts from spin 1.
Yes, that's right. Yeah, so basically, like whenever I say higher spin in this talk, I always mean spin greater than 2.
Yeah, right. But that's why I mentioned that for lower spin, it's also applied.
Yeah, that's right. So yeah, so basically, like the point is, massive high spin particles in general are not ruled out. Next slide. But that does not mean they are free of constraint. The reason there is a constraint is basically there is a conflict between massive high spin particles and causality. So that's the topic of this talk. And this is actually rather well known. First such example was, at least the first example that I know of, is basically the paper by Caamaño, Edelstein, Maldacena, and Zavieda from 2014, where they showed that if you have a tree-level 4-point scattering amplitude, and if you exchange a single massive high spin particle, then that's not consistent with causality. So whenever you exchange high spin particle, you have to exchange an infinite tower of them with unbounded spin. In the second paper, basically like there is a very sophisticated version of the same argument, where just from asymmetric bootstrap kind of argument, one can show that the asymptotic behavior of any such amplitude is kind of fixed. I'll actually discuss this in more detail later. And in the last paper, basically, with my collaborators, I showed that basically, even you don't even actually have to exchange high spin particles. If you have any finite number of elementary high spin particles, as soon as you couple them to gravity, causality will rule them out.
But in the first paper you are referring to, 2014, it was also coupling to gravity or without coupling to gravity?
No, it has to be coupled to gravity. Like so all the arguments is basically when you couple the theory to gravity.
And can I also ask a question here?
Yeah, sure.
So like real world QCD with 3 colors and whatever, 6 flavors and so on with all their masses, it has higher spin mesons.
Yeah.
And they're massive.
Yeah.
And the world looks causal.
Mm-hmm.
So what is the connection to what you're saying?
So
How
the
do you...
third paper that I mentioned here is basically when they are elementary. Like you can like just by doing all the experiment, you'll not be able to tell that if they're even if they're composite, you'll not be able to tell that from the high energy experiments. So basically, at energies larger than the mass of the particle, they behave like elementary particles. So which
but look, I'm not sure, because I'm not sure that the question, if the question refers to QCD, QCD does not include gravity. So in this way, I do not see what is the connection with one to another.
Oh, so there are 2 questions. First of all, you have QCD and it has to be consistent with everything we know of. Then the second thing is, then at the end of the day, I'm going to couple that thing to gravity, obviously, because gravity.
No, but it is still not the same question. That if you have this fundamental QCD, in this fundamental QCD, there is no higher spin, and you can certainly connect it to the gravity, right? So in this way, this issue of kind of breaking causality by massive composite particle does not show up at this level, right?
Yeah, that's right. Yeah, for composite particle, it does not show up.
Yeah.
That's right. So for composite particle, you have to be a lot more careful. Like when so that's why I'll try to make the argument in a very effective filtering manner, so that at the end we can see whether that will apply to large N QCD or not.
Mm-hmm.
Okay. Next slide. Okay, so yeah, so we already discussed this. We know that in large N QCD there are like high spin states, which are glue balls and mesons, which are rather stable when you take the large N limit. So like what's going on? So that's something that I'll discuss at the second half of the talk. Next slide. Okay, now one may ask, like, why should anybody care about high spin particles? Or probably like, why do I care about high spin particles? One reason is basically, as we are all discussing, there are high spin states in QCD, and in the large N limit, they look very stable. So so it's kind of important to know like what's going on there. But to me, the question is kind of more fundamental. So let's say there is some experiment tomorrow that detects, let's say, an elementary high spin particle. What can we conclude from that observation? And there is one more, there is a more broader perspective and broader question that I'd also like to address. It's basically in high energy theory, it's an important question to ask. Basically, can we access some aspects of quantum gravity directly from QFT? So that's a very important question. For example, one might ask, can we derive, let's say, stringy amplitudes directly from QFT consistency conditions? Things like that. So these are important questions, and I will argue, and I basically show there are many evidences that higher spin particles provide a bridge that connects QFT and quantum gravity.
But look, in terms of kind of existence as a nature, okay, all the theory we are discussing, like QFT, whatever, it is not a theory which contain an elementary high-spin particle, right?
Mhm.
So say like Alexei was asking about QCD, but whatever.
Yeah.
So in this way, I'm trying to follow you that that in such theory, coupling to gravity doesn't produce any problem, right? Or it doesn't. It does.
So if for elementary, if like, and when I say elementary, I'll define it properly a little bit later. So
Yeah.
the problem is definitely there for elementary particles, elementary high-spin particles. So
High
when,
spin, right? But in standard model we do not have that.
exactly. So like when you don't have like when you have composite high-spin particles, then basically that's why I'll make the argument very like effective field theory, so that like you can actually see what we mean by elementary, what we mean by metastable, things like that. So then basically when you have composites, then you have to check whether all the assumptions that we are making, they are valid or not. So all the assumptions that we'll make, they are basically very effective field theory assumptions. So like you can just check directly if they are valid or not.
I'm not sure that I follow. To check what? Let's say that we have the QCD and included gravity, weak gravity. Okay, and what we can check?
So those are the assumptions that just I'll discuss like in a couple of slides. Like the theorem that I'll derive first, they will depend on a couple of assumptions, which are those assumptions are basically about like the meaning of higher like elementary or metastable particles. Like what do I mean? Like, do we mean by that? So all the results follow from those assumptions. So those assumptions may, or even for composite particles, they may or may not be valid. It's not that they're always invalid or they're always valid. Like for a composite particle, you have to see that like how the things are working out. Like for example, just to give you some spoiler, for large N QCD, like naively it will look like everything is working, like all the assumptions are valid, but obviously that's not true. So something must come in to actually like make the thing causal, like, but it's not very trivial. So some non-trivial effects actually make the whole thing causal. Okay, next slide. Okay, so this is the first thing that in the first half of the talk, this is the thing that I'll focus on. So this is a physics theorem that I'll prove in the first term, which says theories of stable or metastable high-spin particles can be coupled to gravity while preserving causality only when the gravity sector has many of the properties of fundamental strings. So my first goal would be to actually like explain all these things precisely by what do I mean by the theories of stable or metastable high-spin particles, causality, stringy gravity. I'll explain exactly what I mean by them. And also, obviously, I'll argue that this statement is true. In the second half of the talk, next slide, please. So then I'll show that there is naively there is a conflict between causality and large N QCD coupled to gravity, and I'll explain how that conflict is resolved, or what can we actually say from that conflict.
But I'm not sure, because if you say when you're saying large N, it's large but finite or just or infinitely large?
Okay, so if you don't have gravity, that question is basically N is infinitely large. But when you turn on gravity, that's a very non-trivial question. So I'll actually answer that question at the end.
Okay.
Because like there is two dimensional quantity. One is N, one is basically M Planck over lambda QCD. So when I say large N, when anybody says large N, they have to actually specify large compared to what.
Yeah.
Okay, next slide. Okay, so this is first. Let me just describe what do I mean by theories of metastable high-spin particles. So I have a QFT sector, which is shown in on the left. So they are this GJ. They represent all the particles in the theory. So they at least one of them has spin greater than 2. but there can be particles with spin 0, 1, or 2. Like you can have whatever you like in that set of particles. And lambda QFT is some cutoff scale, and the mass of these particles are much below the cutoff scale lambda QFT. I'm not obviously like this is the way it's written. It's basically an effective field theory description, but obviously in this setup, you can always take. There can be theories where lambda QFT is infinitely large. So then basically it's a complete theory. So that possibility is already included in this setup. And these are the assumptions that I'm making about the theory. So I'm assuming that this set of GJ particles, they describe all degrees of freedom of the theory below the cutoff scale lambda QFT. And second of all, I am assuming that all effective low energy couplings are small. For example, this particular 3-point coupling, that's basically suppressed by some small parameter. It's basically.
But
yes.
If you have large n, it's automatic.
Yeah. So far, like I'm just talking about like general scenario. Like I'm not.
Right. No, the example. Large n QCD is enough.
Yeah. Yes. Yeah. So then the third assumption is basically like the S matrix obeys the standard conditions of unitarity, cosine symmetry, things like that, like all the usual properties. Next slide, please. Okay. So now I take this theory, I couple it to gravity. So obviously the gravity sector has a spin 2 massless particle, which is the graviton. But I'm also keeping the possibility that there can be other particles in the gravity sector. I'm not assuming that there are other particles. I'm just keeping that possibility in this. I'm just including that possibility. So lambda GR, the way it's defined is basically lambda GR is the lightest higher spin state in the gravity sector. So obviously it's possible that lambda GR is just infinitely large and there are no other particles, but like there can be other high spin states. And only thing that I'm assuming is basically the theory, the theory of high spin particles, all the high spin particles, they are metastable even when you couple the theory to gravity. So for example, these GJ particles, they can decay into 2 gravitons. And obviously that's suppressed by 1 over m Planck square, but there can be some coupling constant, let's say lambda G in the numerator. All we're assuming is that lambda G is, it doesn't even have to be small. It's basically order 1. Our assumption is that it's not so large that it breaks down all the entire perturbation theory. So it can be order 1 or 10 or 100, things like that, but it's not perturbatively large, lambda G.
So also I have a question here. So on the gravity sector, your cutoff, you've introduced another cutoff, lambda GR.
Mm-hmm.
And that's to mimic the string scale, which is providing a separate cutoff from M Planck. So M Planck is derived from lambda GR.
Yeah, that's right. So basically lambda GR, like morally speaking, you can think of lambda GR as the string scale, but since I'm not talking about strings, so it's basically like, to me, from a quantum field theory perspective, it's basically the lightest high spin state.
Yeah, but then lambda GR, it's something like thin Kauppin multiplied by Max Planck mass or something like that.
No, lambda GR, like morally speaking, it's the string scale.
Yeah, but Arkady is saying that. But Arkady is saying that M Planck is derived from lambda GR, right? So
or other way around. If I'll say that lambda GR is thin Kauppin multiplied by Max Planck mass. No, I mean to say to have this another scale. I mean that the difference between the scales could be associated with thin Kauppin. Is what I'm asking.
No, so far I'm not assuming any of that. They can be, like they may not be. It's to me that M Planck scale is basically set by the just by the gravitational interaction, and the other scale lambda GR, I'm just assuming there can be other states in the theory.
No. But this other scale should come from something, because in gravity itself you do not have anything but Planck mass, right? That's it.
Yeah. So that's the lambda GR is I'm defining it as the lightest higher spin state in the gravity sector. So that's the definition of lambda GR. So below lambda GR, there are no other states. Like, so basically, if you're looking at scatterings much below lambda GR, the scale lambda GR, then all you see is basically exchange of gravitons. That's it.
Mhm.
So when you hit lambda GR, you'll see that like there are other high spin states that are exchanged.
Right, but it is kind of modification of gravity then, right?
Exactly. Yeah, it's modification of gravity. But again, to let me emphasize that, like, I'm not assuming that there has to be some modification so far. I'm just assuming that if there are modifications, that's already included in the setup. Okay. Next slide, please. Okay. So now this one might ask, so what do I mean by like other states in the gravity sector? Like how do I differentiate between states in the QFT sector, states in the gravity sector? So let me give you a precise definition of that, like precise definition of what do I mean by other higher spin states in the gravity sector. So let's take any GJ particle you like, and let's just look at a 2-to-2 scattering amplitude of that GJ particle. First, let me make M Planck to be infinitely large. So basically, since like we are in the weakly coupled regime, the tree-level scattering amplitude is a meromorphic function with simple poles, and these simple poles are located at the position of all these GJ particles. Like since like they are all the degrees of freedom of the theory. So if you look at the amplitude, you'll see poles that correspond to this exchange of these other GJ particles. Next slide, please. So now let me make M Planck to be finite. So what happens is that when you make M Planck to be finite, the amplitude will develop at least one more new pole, which corresponds to a graviton exchange. It has to, like that's fixed by the soft theorem. So what might happen that the amplitude might develop other poles. So these other poles, when you take the limit M Planck to infinity, these other poles will also disappear. So when I say other states in the gravity sector, what I mean is basically the 2-to-2 scattering amplitude will develop these additional poles when M Planck is finite. And my argument at the end will basically be to show that these additional gravitational poles are essential to the preservation of causality when you have these higher spin metastable particles. Next slide. Okay, so this is the outline of the talk. Let me pause for questions, or I'll just proceed. Okay, next slide. Okay, so the causality obviously will play a very important role in this discussion. Causality is actually a trivial statement in classical physics, even in quantum mechanics. But in QFT, causality is a rather non-trivial statement. The reason is the following. In QFT, causality is a statement about operators. So it says basically, if you take two space-like separated operators, their commutator must vanish. And since it's an operator statement, you can just take this operator, you can insert this inside any correlator you like, that correlator must also vanish. So basically, that means this statement actually gives you an infinite number of consistency conditions that any QFT correlators must satisfy. So that's why it's a really non-trivial statement in QFT. Next. Before I proceed, I want to emphasize these two important points about causality in quantum field theory. They are well known, but still I want to emphasize them for a few seconds. Requiring a QFT to be causal in every state of the theory does impose non-trivial constraints on QFTs. And the second point is, QFTs that appear to be causal in flat spacetime can violate causality when coupled to gravity. Okay, next slide, please.
When you are saying coupled to gravity, you mean if it's a weak gravity, like you know, kind of at the level of say having this graviton pole, then you still have this kind of normal propagators, right?
Yeah.
And they satisfy this condition and perturbatively, I mean.
Yeah.
So you mean perturbative statement, or you mean non-zero gravity in a sense that like a background field?
No, it's basically like I'm treating graviton as a like spin 2 particle in the KFT.
Say it again.
So basically, I'm treating like gravity as a like spin 2 massless spin 2 particle in the KFT sense. So it's not just background gravity. It's basically like poles in the poles in the amplitude, scattering amplitude, things like that.
Right. So you mean gravity is inside as a propagator of graviton, or
right.
gravity? You see, because if I have a background of gravity, then the notion of causality becomes different, right? I mean,
yes, yeah. It's not that. It's basically so the statement is about a 2-to-2 scattering amplitude. So which involves an exchange of graviton.
I see.
Okay. So this slide, I'm not going to explain this slide at all. This slide is, I'm showing you this slide just to emphasize the point that just imposing causality in quantum field theory can give you a lot of non-trivial results. So, this, I'm not going to explain any of them. This is just to show that that requirement is non-trivial in quantum field theory. But the important point is, if you try to apply the condition about the space-like separated correlators, space-like separated operators, you need to compute position space correlator in QFT, which is in CFT, you can do that. So that's why most of these constraints are in CFT. But in QFT, that's a very hard thing to do in general. In QFT, we don't actually compute position space correlators. We compute scattering amplitudes. Next slide, please. So there is a version of the causality condition even for scattering amplitude. So this is morally analogous, but actually this is not exactly equivalent of the previous statement about causality. So this is basically a statement about 4-point scattering amplitude. So let's take any 4-point scattering amplitude you like. S, T, and U, they are the standard Mandelstam variables, and we are looking at the regime where S is much, much larger than T and mass square of all the external particles. Next slide, please. So now, given that amplitude, I can go to the impact parameter space by integrating over the transverse coordinates. So by doing that, I can define this quantity delta, which is also known as the phase shift. So this phase shift has some really nice properties. For example, at tree level, one can show easily that the phase shift is completely determined by the T-channel poles. So contact diagrams or other channels, nothing else will enter in the phase shift. So if I know all the T-channel poles and the residues, I know the exact phase shift. Next slide, please. Another important property of this phase shift is basically physically it's related to the Shapiro time delay. So one expect that this thing should be positive. Next slide, please. And there is actually a very rigorous, a more or less rigorous argument that one can make by mapping an iconal scattering to a signal transmission problem. So basically what you can do, so basically let's say you have some in-state which do not have any support for negative V, where U and V, they are the light cone coordinates. And something happens in between and you have some out state which is shown in green. So if your in signal does not have any support for negative V, the out signal should not have any support for negative V as well. So just from this statement, you can derive some boundedness and some analyticity condition on the iconal phase shift. Next slide, please.
No, but yes. I'm sorry, but a canal implies that you are summing something, right? Let's say that we can limit ourselves by T level amplitude. Then I can write a dispersion relation for this amplitude, right? At T level,
yes.
Right? And I would say that at the T level, I do not have, any causality breaking, right? Because I mean, all this propagator as a normal propagator, the dispersion relations are okay, and dispersion relations are based on causality, right?
This is kind of different. Like that's not entirely true when you have your external states are high spin states. So basically, it's for scalars, it's automatic, but
Yeah.
for external high spin states, it's not.
No, what means not automatic? If you have, say, you mean high spin in external legs or high spin of exchange?
External legs.
External legs.
Yes.
I see. Because if it's not external legs, then high spin is okay, right? Because it is still normal propagator, right?
Yeah. So, but the thing is that, like, when you impose the positivity of the phase shift, actually, you can, like, it's not obvious probably to begin with. So when external states have spin, and because you can tune your external spins or the polarizations, actually satisfying this positivity condition, it's not trivial. Like, so for
I see. Yeah, no, I understood what you're saying, talking about, but then still I'm wondering, this phenomenon you are talking is when you are saying that it is a canal. To me, a canal implies that you are repeating, that you are summing up certain amplitude. It's not tree level, right? So is it important or not?
Okay, yeah, so that's a very important point. So generally, when people talk about Eikonal limit, they generally think of like summing over ladder diagrams, and then the entire amplitude exponentiates. Then it's very easy to think of that as the phase shift, and it's very easy to argue why that has to be positive, things like that. But the argument that I made using the signal transmission problem, it's basically, it does not actually require that the tree level amplitude exponentiates. It does not require that at all.
Yeah. So you can see phenomenon at the level of tree amplitude already.
Exactly.
So then you do not need this delta. Then you can see this phenomenon even without introducing this impact parameter, whatever, right?
No, actually not. Like no. So it's different from, like, the thing that you're probably thinking of is basically like the unitarity condition from like crossing, things like that, which gives you some positivity condition. This is not exactly equivalent.
I see. But then you are saying that just to write dispersion relation at tree level, it would be a problem for high spin external particle, right?
Yes, that's right. Yeah. Yes.
No, I'm sorry to interrupt, but I'm just trying to follow.
It's a very important point, actually. Like, so this positivity conditions, which were initially pointed out by Kamahu, Edelstein, Maldacen, and Zaviadov, they are actually like, they are completely independent of like all the unitarity dispersion relations, things like that.
I see. Yeah.
They look similar, but they have more content. Like, for some scenarios, you can actually map one to the other one, but it's not that they are completely equivalent.
I see. Okay. So, thank you.
Yeah. So their conditions is basically the following. First is basically they showed that the phase shift must not grow faster than linearly in S in any regime for S. And the second thing that they showed is basically when the phase shift grows linearly in S, it has to be positive. And this phase shift, as I said earlier, it's basically computed from the tree level amplitude. So these are actually things that you can actually compute in any quantum filter if you know all the tree level diagrams. Let me mention it again. So this, I don't know of a way to actually derive these two conditions directly from the condition about commutators of space-like separated operators must be zero. So I don't know of any easy way to actually relate one to the other one, but like both of them, like both must be true for causal theories, but for I don't think anybody tried to actually map one into the other one. But there is a very nice thing that you can do in ADS. In ADS, you can actually show that if you violate these two phase shift conditions in the bulk, on the dual safety side, commutators of space-like separated operators, that becomes non-zero. So in ADS, you can actually map one to the other one in a really nice way. Next slide, please. Okay, so now we have all the ingredients to actually derive the statement that I mentioned in the beginning. So I'm considering theories of metastable higher spin particles coupled to gravity in 4 spacetime dimension. Next slide, please. Basically, I'll perform 3 thought experiments. Let me explain the first one a little bit. It's basically, I have a higher spin GJ particle and a graviton coming in. They exchange a single graviton, and I have the same GJ particle and the graviton going out. So that's the first scattering that I'll study.
But for this scattering, it should be other diagram as well, where there is no exchange of graviton. Where is this diagram?
Oh, okay. So there, you are basically saying, what about other GJ exchange of other GJ particles? Or because that's the only thing.
No, not exchange. Other particle means the same. In external particle, you couple graviton to them twice. No, I mean, okay, it goes as this line, and you couple graviton to particle G once, and then propagates particle G itself, and then couple graviton again.
Yeah, so basically this is the leading amplitude. This is the 1/m Planck square amplitude. Like everything else that you can write down, they are suppressed by something else, because
no. Yeah, in terms of coupling, it is the same power. I have to 1/m Planck square in both cases. No.
What the other? Can you explain the other diagram, please? So what are you exchanging in the middle? That I missed that.
No, not exchanging in the middle. You have T channel exchange, not S channel exchange.
Okay, yeah, I understand. So basically, like as I said earlier, if you want to compute phase shift, only T channel poles matters. So other channel poles you can just show very easily, like they don't contribute to the phase shift.
Yeah. So this T channel exchange is okay with you, right? So yeah. I mean, it's also present, right?
Yeah, yeah. So this is okay. So when I draw these diagrams, it's basically I'm just drawing the diagram that will contribute to the phase shift. That's it.
I see.
Okay, so that's the first experiment. The second and third, they are basically some souped-up version of the first experiment, where basically I'm just in the first experiment I have all the external states are single one particle states. For the second and third experiment, is basically the external states are not one particle states. They are some coherent state which are created by superposition of multiple states. So I'm not going to. So basically, okay. A more formal way of thinking of this is the following. The first experiment one can think of is basically defining some kind of positive inner product, and the positivity of the phase shift is basically the statement that norm is positive.
No, but I still can, okay, maybe you will explain it later, but still my impression was always that T channel exchange is the one which defines asymptotic at large S, T channel exchange, right? And yeah. What you are discussing, it is S channel exchange, right? And it is
okay. So now probably like my definition of T, like what I mean by T channel is probably like it's different than what you're thinking about. It's basically, when I say T channel, is all I mean is basically like the channel where basically like the diagram that's shown in for experiment 1. I'm just calling it T channel diagram.
No, I understood that, but what I'm trying to say is that at large S, I thought that the asymptotic at large S, at large energy, is defined by T channel exchange, not by S channel exchange.
Yeah, but so okay, so the order of limit is basically you are first computing the phase shift, then you're taking S to be large.
Yeah. Okay.
Yeah. So yeah, so the T. Yeah, I see your point. Yeah, so with those diagrams, when you compute the phase shift, you'll see that they grow as T square, but they'll drop out.
Mm-hmm.
Okay, so I'm not going. I'll not go into all the technical details, like how to actually. I'll just briefly sketch how to actually derive any constraints out of this. All the technical details you can find it in our paper. It's basically. The goal is basically just to consider this 3 set of experiments and impose positivity of the phase shift. The second and third experiments, you can actually think of them as some kind of Cauchy-Schwarz inequality associated with a positive inner product, which is given by the phase shift. Next slide, please. The reason actually you can say anything just from this experiments is the following. I actually already mentioned it, is basically since the phase shift is determined by T-channel poles, you can very easily show that phase shift is basically given by a product of on-shell 3-point amplitudes. On-shell is very important. So if I know both, like as soon as I know two vertices, I can just write down the phase shift just from that information. And the nice thing is on-shell 3-point amplitudes are completely fixed by Lorentz invariance. So basically I can compute this phase shift just up to a couple of coefficients which we can determine from the positivity condition of the phase shift. So basically the goal is to actually tune all the polarizations that I have, impose positivity of the phase shift, and impose bound on these undetermined coefficients. So far I haven't assumed anything about those coefficients, and I'm not even going to assume anything about these coefficients. Just from yes.
But this log, if you consider this S channel, then it means in terms of how say, in terms of angular momentum, it is limited number of angular momentum, right? Which is the present. So how logs appear? Because a log of 1 over b appears usually because you have like a T-channel exchange where you have different momenta, and here you have, if you consider your S channel diagram, your momenta is angular momenta is defined by spin of this intermediate particles, right? So it's not more than 2 or something like that.
Okay, can you not more than 2?
No, because you have here you have graviton inside, right?
Yes, that's right. Yes.
Okay, graviton it is angular momentum equal to 2. I mean, if I am considering.
Oh yes. So basically, it will go as like S square. So
right, but the log appears then because often log appears because you are summing up over angular momentum.
In this case, is basically the log appears just from like, since you are going to the impact parameter space by integrating over the transverse direction. So that's how the log comes from.
So it's a log of something like S, log of S, or what, in terms of
no. For graviton exchange, just the impact parameter amplitude goes as S square log b. And basically, like since the phase shift is defined as like 1 over S of the amplitude, it's basically the phase shift goes as like S times log b, something like that.
Right, but you see, b is conjugated to angular momentum, right?
Yes, but so that
and your angular momentum is limited by 2. So so that's why I'm asking.
So the actually, like when you the way the phase shift is actually it goes is the following. It's basically it's S to the power spin of the exchange particle times basically some function of b.
Right, but yes. But let's say instead of b, I could introduce angular momentum, right?
No, b basically b in the relation between b and angular momentum is not that linear in this case. So it's basically the angular momentum will always appear with S, like it's always S square or something like that, like S to the power j minus 1 something like that.
So then you are saying that there are a lot of angular momentum, even in spite of the fact that your exchange goes by 1 particle with spin equal 2, right?
Yeah. So even like, let's say if you have like a scalar and you exchange a scalar, so even then you'll have that log b. So, okay. So the log b doesn't. It's basically the log b is there for like any exchange. It's basically
So in this way, it's this b is not that kind of simply related to this angular momentum, right?
No, it's more like the IR divergence that you get in 4D. So it's basically it has that information. That's it.
I see. Okay. Thank you.
Yeah. So now I can just compute this phase shift for and for all the three experiments that I mentioned, and I can summarize the result in the following slide. Okay, so this is like after doing some long computations, I can like phrase everything in this particular way. So only way you can make sure that the phase shift is positive for all possible choice of the external polarization is basically this 4-point amplitude where you have GJ graviton going to GJ and graviton by exchanging one graviton. That the phase shift associated with this amplitude is it violates causality unless you exchange other higher spin states along with the graviton. So, and not just that. So basically these additional states, it's not at this point, they are not no longer, it's not that you have any choice. If you have external high spin states, you have to have these high spin states in the gravity sector. That's the only way you can actually make everything causal. Not only that, from our analysis, we can actually even found a parametric upper bound on lambda GR. So that basically I'll explain next. So yeah, so
but it look because you can consider this G particle to be free particle, right?
Yeah, even then it's true. Yes.
Yeah, because you are not using any interaction between them, right? I mean, without gravity, right?
That's right.
So then what you are discussing, it essentially it's about gravity, not about anything else.
That's right. So basically, even if you give me a single free massive high spin particle, whatever I said, that still true, and that's why it's kind of surprising to me.
Mm-hmm.
So to make it even more general, since I did not assume anything about the high spin theory, let me just now parameterize that theory by its amplitude, so that like I can actually show you that you can derive a more precise bound on lambda GR. So let me parameterize this 4-point GJ scattering where like all the external states are the same GJ particle. So now you have like an exchange of graviton. Also, you can exchange like other GJ particles in this particular scattering amplitude. So the first term that I write down on the right hand side, that's from the graviton exchange, and that's yes.
I'm sorry, but let's say that there is no non-gravitational part. But how it looks like, because if I will add T channel exchange, right? This exchange by a particle itself, I mean by G. How it appears in the amplitude, it's a different part, right? I mean,
yeah, so it's basically that part I'm parameterizing that by the second term. So since
so second term would describe T channel exchange.
T channel exchange of other GJ particles.
Not but what means other? It could be the same GJ particle, right?
Yeah, by other I mean like this from that set. So it's not the graviton, like everything else.
Yeah. Okay.
So the second term is basically just to parameterize like the non-gravitational part of the interaction of the GJ particles. Mm-hmm. So the second term comes from just from the QFT part of the theory. So the reason I'm writing it down as like the gravitational part and non-gravitational part is the following: the relative strength of these two interaction will actually give you different bounds. That's kind of interesting. So,
no, but look, T-channel exchange, I would not call it non-gravitational. It is still gravitational part.
Oh no, okay. So probably again, it's I guess like our definitions are a little bit different.
Yeah, because I'm not introducing any new interaction, only gravity, right?
Oh no. The second term is basically like if I turn off gravity, so the phase shift that I get for this 4-point amplitude, that's the second term.
Okay, I got it. Yeah.
Okay. Next slide, please. Okay, so when the gravitational part of the amplitude is larger than the non-gravitational part of the amplitude, so we can derive something really strong. It's basically for all high spin particles, the lambda GR has to be smaller than the mass of the external high spin particle. So this is completely fixed by the mass of the external particle. And that immediately means is basically like there cannot be any QFT description. So for example, if I just think of integrating out all the high spin states in the gravity sector, then I can no longer do that. So there is no QFT approximation in that sense. Next slide, please. Now, in the other limit, where the non-gravitational part of the amplitude is larger than the gravitational part of the amplitude, now basically, lambda GR can be parametrically larger than the mass of the external particle, but still it's far below the Planck scale. So now it's basically given by this expression shown in red. It's a parametric bound which all the particle in the QFT, all the high spin particle in the QFT sector, they must satisfy this bound. So basically lambda GR has to be small enough such that this is satisfied by all the particles. Next slide, please.
Oh, sorry. So what was this little GJ coupling again? This is it's not
it,
related. It's not related to the gravitational coupling. I mean,
no, it's basically it's the part of the non-gravitational coupling. So if I turn off gravity completely, and I consider like a 4-point scattering amplitude of the same GJ particle, it's basically that GJ, this small GJ is basically the strength of that.
Yes. So this is an interaction between massive higher spin J particles.
Exactly. Interaction between massive high spin GJ particles without gravity. Like this is the non-gravitational.
Yeah. But the key here is that they're massive, right? Because if they were massless,
yeah, that's right. That's very important. Yeah,
there would be no interaction, right?
Yeah, they have to be massive, because the massless one they're already ruled out by Weinberg-Witten theorem. So like that,
exactly.
everything here they're massive.
Yeah, because that's right. These were ruled out a long time ago. You can't have massless. It's basically the fact that interactions require higher spin gauge invariance, which is not possible.
Yeah. And actually, even from our analysis, if we just try to make it massless from the beginning, even we can rule it out like just from causality. Like we don't have to do much. Like it's almost automatic.
How do I see it in your formula? I should be able to see it, right?
Oh no, not from the final formula. You'll not be able to see it. Like the reason is basically like when you start with a massless particle, like all the 3-point amplitudes that you can write down, they have different structure when they're massless and when they're massive. So it's not that like you can just take the start with massive particle. You cannot take the massless limit. You have to start.
Yeah, sure. Yeah, it's discontinuous. No, you're right.
Yeah, that's right. So like if you start from massless particle to begin with, you can just from the positivity of the phase shift, you can just rule them out immediately. Like it's very easy to do.
Okay.
Yeah, but Tony, I trying to change the formulation because it's not gauge invariance. It is a statement that massless particle possible only if you have conserved sources for them, and that's why it's limited by spin 2, because the only conserved sources, it could be either kind of for boson, it could be either conserved current or conserved energy momentum tensor. And gauge invariance is just a technical trick how to use it, but essentially it is a necessity of the conserved source.
I see. Yeah.
Which doesn't exist for higher spin.
Right. I see. Thanks.
Okay. Next slide, please. Okay. How much time do I have? I'm running a lot behind.
So I personally have to leave at 4:50, but that doesn't mean the talk necessarily has to.
Yeah, I mean,
Tony, Mateos, what do you think? Yeah, you started like 10 minutes late anyway.
You started at 4:40, 4:45. So you have another 10 minutes, 15 minutes. Don't worry. Yeah.
Okay. Yeah. Okay. This slide is just to show you graphically like the previous bounds. And I'm basically showing you the free particle at the left. It's basically, if you, as I said earlier, if it's a free high spin particle, like there cannot be any parametric separation between lambda GR and the mass of the particle. Next slide, please. Okay, so this is the first part of the theorem that I just showed. Higher spin metastable particles cannot couple to gravity while preserving causality unless there exist higher spin states in the gravity sector much below the Planck scale. Let me now move on to the second part. Actually, we just by knowing that there are higher spin states in the gravity sector, we can actually say a lot more about the underlying UV complete theory by making some assumption about the S matrix of the full theory. Next slide, please. Okay, so since there are higher spin states in the gravity sector, so that means basically, even if I take any like arbitrary scalar from the theory, and if I just consider like a 4-point scattering amplitude of that scalar, since it will obviously interact gravitationally, so it will exchange a graviton, and since these other particles they have to be there now, so that means basically if I consider a 4-point scattering amplitude of this even a scalar psi particle, they will exchange not just graviton but this entire tower of higher spin states. Which next slide please. So this is very important because now I can actually use a very nice, a really elegant uniqueness theorem by Karen Huot, Komorgotsky, Sever, and Zaviev. So just from some S-matrix bootstrap argument, they showed something really important. They basically showed that if you have any 4-point scattering amplitude of scalars, and if you exchange if you exchange high spin, massive high spin particle in that amplitude, then obviously, first of all, as I said before, you cannot have just one single exchange. That means basically you have to have an infinite tower of higher spin states with unbounded spin. Otherwise, it violates causality. So that given that information, they basically showed that if you exchange an infinite tower of higher spin states, the amplitude for large T and S has to be unique.
But I'm sorry, but your higher spin states are not the higher spin associated with original higher spin, it's associated with gravity, right?
Yes, exactly. So now basically,
so in this way, it's kind of I'll say from different channel. If you know, I mean, I don't know.
Basically, like since from first argument basically tells me that there are these high spin states in the gravity sector. Now I completely forget about the KFT sector. I'll just focus on the gravity sector and see what I can say about the gravity sector. Okay, next slide, please. Okay, I'll actually the way I can use their theorem is basically I'll assume this like standard conditions about the full S matrix of the full theory. I'll assume that like it's weakly coupled, unitary, crossing symmetric, and it has the standard Regge behavior for large S and large T, and there is no accumulation point in the spectrum. Basically, like it has some, it has well-behaved thermodynamic limit. So these are the assumptions that were made in the original.
But accumulation point at infinity are included because you can have this Hagedorn or whatever. You mean or what kind of?
No, it's basically for okay. The assumption is basically for any finite energy scale, there are finite number of states below that.
Okay, so Hagedorn is not allowed, right?
Yeah. Next slide, please. So just from this assumptions and by using the CKSZ uniqueness theorem, we can say the following things about the gravity sector of this full UV complete theory. So the leading Regge trajectory has to be asymptotically linear. So basically, like it's proportional to T for the slope is given by alpha prime over 2, and alpha prime for is basically is given by 1 over lambda gr square, which, as I said earlier, it has now it has a upper bound. Next slide, please. So this linear Regge trajectory also implies that if I look at imaginary part of the impact parameter amplitude for large B, it's small, but it's non-zero. So since this is the inelastic part of the amplitude, this immediately means that there has to be extended objects in the theory. And this, we can actually estimate the size of these extended objects. They are basically given by this square root of alpha prime log alpha prime s. The reason this is very nice is basically this is exactly what you expect from string theory. Next slide, please. You can actually say a lot more. Just from their theorem, we could show that the gravity amplitude, or basically amplitude associated with gravitational interaction for large S and T, large and positive S and T, it has this fixed structure. So it's exactly what it's written. If you look at this expression for long enough, this is exactly the tree level gross Mendel amplitude. Next slide, please. So this is basically the large T, large S limit of the 4-point closed string amplitude. So basically the gravitational part of the gravity amplitude for large T and S must coincide with the tree levels closed string amplitude. Another way of saying this is basically, next slide, please. So the theory for has an infinite tower of Regge trajectories, which are asymptotically linear, parallel, and equispaced, which is exactly what you get from tree level closed string theory. Next slide, please. So basically, that means we can identify lambda GR as basic some kind of effective string scale, and that immediately means the bound on lambda GR that we had from the first part of the talk, that gives you a bound on the string scale. And this is shown here. And obviously, string scale has to be low enough such that this bound is satisfied for all GJ particles that in the QFT sector.
And is there a uniqueness here? I mean, is it uniquely string theory, or is there some freedom still to be?
That depends on what you mean by string theory. So the asymptotic amplitude is completely fixed. Now, one may say that like probably it comes from not a string theory, but something else. Fine. It's basically, it should like at least the amplitude in that limit should look like a stringy amplitude.
Uh-huh.
So because basically like my entire argument is basically based on like effective field theory, like perturbative effective field theory arguments. I have no way of actually saying they're strings or not. All I can say like how the amplitudes behave, how the Regge trajectories, what are their behaviors. I can say only those kind of things from our argument.
I see.
Next slide, please. Okay, so basically the full theorem is the following. So in the first half of the theorem, I showed that when you have theories of metastable higher spin particles coupled to gravity, additional gravitational higher spin states are essential to the preservation of causality. Then I utilized the CKSZ uniqueness theorem to show that any weakly coupled UV completion of such a theory must have a stringy gravity sector, where by stringy gravity sector, I basically mean the things that I said before about Regge trajectories and the amplitude, things like that. Next slide, please. I have like a couple of minutes. So now you can ask me like what about large N QCD or any large N confined gas theory in 4D, because they have metastable glue balls and mesons of arbitrarily large spin. So what it means that large N QCD, like the naive way of thinking about large N QCD coupled to gravity, it has some limitation. So basically, when you couple large N QCD to gravity, there are some subtleties, which I'll explain in a couple of slides. Next slide, please. So as we already discussed, so if you in the large N limit, all the interactions are basically suppressed by 1/n. So that means that the statement about metastability that applies. So all the pions and all the mesons and glue balls, everything are everything behave as if they are more or less free particles with higher spin, which are stable or metastable at least. Even the gravitational couplings, they have the same, they have the structure that we discussed in the first half of the talk. Yeah, go ahead.
But it is amplitude without graviton, right? Here it is below. I see.
Yes. Yeah.
Okay.
Okay. Next slide, please.
One, it's a normal one. I see.
Yes. Yeah, that's right. And next slide, please. Okay. So this part of the argument actually is exactly the same. So if you look at this particular process where you have GJ particle in the which is now a glue ball, and you have the graviton on the right hand side, again the same statement is true. Additional T-channel poles are essential to the preservation of causality. That statement is still true. Next slide, please. Now, the thing that's important is basically how to resolve that conflict. And one thing that actually I did not mention, which is actually very important, the theorem that I mentioned in the first half of the talk, there are many variations of this theorem that I could derive. Just because like I can just change some of the external states, like there are many different variations which are there, and obviously all of them should be consistent with causality. So basically, just by looking at all these possible scenarios, we could conclude that there are exactly two possible resolutions of this conflict. One resolution is actually the causality violation is cancelled by like higher spin states in the gate sector. By that I mean like other glue balls, higher spin glue balls, things like that. I'll explain how that's possible. The second scenario is basically, since the problem is created by the graviton exchange, probably like high spin states in the gravity sector should resolve the problem. That's the second possible scenario, and these are the only two possibilities. Next slide, please. The reason the gate sector actually can resolve this problem is the following. If you look at like, since the glue balls are not, they are actually composites, there is some signature of that in the interactions. For example, as GJ glue ball can actually decay into two gravitons, which is basically not N suppressed, which is N enhanced. So generally, we don't actually think about this kind of interactions because they are not important for any of the experimental stuff. But this is this decay is actually enhanced, which is very important. Now, also there can be some mixing between spin 2 glue balls and graviton, which is also N enhanced, which is very important. So not only that, they can be there. It's not that they're allowed by large N counting. Actually, you can write down some rules which will show you that this mixing between spin 2 glue balls and graviton, all of them cannot be zero. So some of them have to be non-zero. So the way these interactions can actually restore causality is basically, first of all, both these two types of interactions should be there, and not just that, they have to be highly fine-tuned. So since these amplitudes are not exactly known, so I will not be able to tell you how what do I mean by highly fine-tuned, but so they should be, it's not that any generic choice of these interactions will actually solve the problem. They have to be so fine-tuned that they can actually cancel the problem created by the graviton.
Just one moment. Can Mateusz, can we switch to you sharing the slides, starting with slide 48?
Yep, sure.
Thank you.
Let's see if I can.
Sorry about all the trouble.
Yeah, because Sandepan, because I'm gonna have to leave at 5 as well, because we have a I'm on the same committee that Alexi's on.
Yeah, I can actually let me do.
But you have 5 minutes. I think you can probably finish up.
Yeah, I think 5 minutes it's good for me. Yeah.
Yeah, because we have the same committee at 5.
That's right, and I need to do something right before, so I'm going to have to leave very sharply in a couple of minutes. But Sandepan, this is a wonderful talk. Thank you.
Yeah, thank you very much. Yeah, sorry for all the trouble. You have been doing half of the work.
But when you are saying that free masses spin 3 half particles rule out, but without anything this there is no possibility to organize masses 3 half particles because there is no conserved current if it's not supersymmetry.
Yeah. So basically, yeah. So just from since my analysis does not know anything about supersymmetry, it's just it just follows from the argument.
Right, but module supersymmetry, 3 half masses particle are excluded anyway.
Yeah. And also other implications are basically classical shock waves are ruled out, spectating particles are ruled out. I don't want to go into detail by what I mean by spectating particles. Is basically any particle which can generate a classical gravitational shock wave, that's not allowed. So since there is a mixing between glue balls and gravitons. So basically like things that are expected from like classical GR backgrounds, like they are more subtle in this case because of this mixing. Next slide, please. And it's also like one might also think of actually like solving this problem created by the graviton exchange by just adding higher spin states in the gravity sector. Obviously, as I mentioned in the first half of the talk, that will solve the problem. Not just that, it's basically like it now gives you a bound on the string scale in terms of like n, lambda QCD, and m Planck. Let me not go into yeah, this is basically this just follows from the theorem that I mentioned in the first half of the talk. Next slide, please. Yes.
So how does the ADS, if you model what you did in the bulk with ADS, how does ADS solve which one does it pick? The gravity
that's a very good question. In ADS, actually, we found something rather remarkable. In ADS, like you have less options. So for example, like as I said in the first half of the talk, even here, like in flat space, there can be, after some fine tuning, there can be some parametric separation between the string scale and the mass of the higher spin states in the QFT sector. In ADS, that's not true. In ADS, basically, whatever the mass of the external particle is, that's what the string scale is.
So it modifies the gravity sector then in ADS.
Yeah. And we are not very sure why that's happening. Like there must be a very good reason, but like we don't have a very good understanding why. Like in ADS, we are getting a little bit stronger bounds.
I see, but you're modifying the gravity sector. That's what ADS chooses when you model this in the bulk.
Yeah.
I see.
And okay, and a unifying feature of both these scenarios is basically for weakly coupled gravity, the theory must have a stringy description when n is above m Planck over lambda QCD. So for both these resolutions, like both of them imply this statement. Next slide, please. So now let me just conclude. If you want to take away only one thing from this talk, that's basically again something that probably was well known, especially QFTs that appear to be causal in flat space-time can violate causality when coupled to gravity. The thing that's most surprising to me is basically like some aspects of quantum gravity emerges from perturbative QFT. That I still find it very surprising, and probably I should not be surprised because of ADS safety, but this emergence of like strings just from like perturbative quantum field theory, that's still very surprising. I don't fully grasp its implications. I also argued that theories of metastable high spin particles can be coupled to gravity while preserving causality only when the gravity sector has many of the properties of closed strings. Our argument implies that the gravitational interaction in any confining large N gauge theory must be accompanied by interactions involving other higher spin states well below the Planck scale. And as I showed that this has some surprising implications for large N QCD coupled to gravity. The large N QCD coupled to gravity is more subtle than what one might naively expect. Thank you very much.
I'm trying, okay, in the sense that it's not a lot of time, but let me still ask, because my impression is following people like Waffer and others that the statement that, in the presence of gravity, quantum field theory could not survive. It is more generic. It's not associated with high spin, but it is more generic, right? So in this way, if you believe that it is the case, right, that you need kind of thingy type of approach anyway, right, then your example with high spin, it's only it's only kind of partial part of the argumentation, because if there is a more general one, then of course it's okay with this, but then you would have it even without having high spin particles, right?
Yeah, I completely agree. Like if you thinking from the perspective of string theory quantum gravity, then you should say that this is a very generic feature that should be there.
Yeah.
But the reason it's kind of surprising to me is basically since if you start thinking from the QFT side, it seems to be like almost like from the QFT side, one would just think that probably whatever is allowed can be there. Like there should not be any bound from like weakly coupled gravity as such.
Yeah.
But even from the perturbative QFT, you're getting statements which one only can expect from like quantum gravity. That part is surprising. For example, like I did not mention in the talk, so we get a weak gravity conjecture out of this analysis for high spin states. So obviously, like from if you ask string theorists, they would say probably this obviously this has to be true for any particle, not just high spin particles.
Yeah, right.
But like for our analysis, it follows automatically for high spin particles.
I see. No,
So,
but look,
yes.
I think that in certain way, okay, one of formulation of this weak gravity, whatever, is that when you consider gravity, then this separation, because normally in quantum field theory, we imply that there is kind of, upper scale, like a cutoff of QFT, and then you can start from kind of point like whatever theory at scale at cutoff, and then go down for a smaller scale.
Yeah.
When they talk about gravity, they are arguing that essentially the infrared scale becomes undistinguishable from this cutoff scale, and then you do not have a kind of a window for quantum field theory, right?
Yeah,
So-
that's right. Yeah.
So you need your extended object from the start, right?
That's right. Yeah.
And then, of course, it includes higher spin as well. I agree, right? Because it's natural, but looks like appellation goes to kind of more fundamental argumentation, right, than just high spin.
That's right. Yeah. I completely agree.
I see.
Yeah. So it's the surprising part for us was basically like if you can say anything from effective field theory itself, like that was the surprising part.
So can I quickly ask a question before I have to go? I mean, this limit, this bound that you got on N and M Planck, is that a bound? Can you replace that with a bound on G5 and the ADS curvature?
I did not check that, but probably you can. But I don't think I have any precise answer, but I don't see why not. Like it should be possible.
Yeah, but then it could be just trivial from the ADS point of view. It just says that G5 squared K is just less than 1. I mean, just some perturbative argument, you see, that's why.
Yeah, so since the ADS argument is more constraining, a little bit more subtle, so like that's why I'm hesitating to answer the question. So probably like I can say things which are not true, but so a version of this in ADS, even in our paper, there is a section where like we explain like what happens in ADS. There, yeah, it's but I cannot. I don't think I can convert that into a bound on RADS and G5 immediately. Like it might need like a couple of steps, which I don't.
Yeah, because I mean, you can easily do it from the N is related to 1 over G5 squared, and then the M Planck is related to the curvature. So there's an immediate relation you can just take from what you have already. But
no, this is for the fat. So in ADS, it's more constraining. So that's why like I see. Yeah, so that I have to. Yeah, so the ADS, and there is one more thing that we also should be more careful about in ADS. It's basically in ADS. Again, you have one more extra scale that RADS, and there it seems that there is some like interplay between like RADS and like now you have like multiple dimensionless quantity. Like you have N, you have like M Planck over lambda QCD, you have lambda QCD times RADS. So now depending on like which regime you are in, you might get different bounds. Yeah,
but the K, the curvature scale could play the role of your lambda GR, you see.
Okay, so there
Anyway, I'm sorry because I have to go because
Okay, yeah, I'll think
No, no.
about it.
because it's like it's an exam, an oral exam that I have to appear at.
No,
But
no,
thanks
right,
very much, Sandipan. It was a very nice seminar, very nice, and thank you very much. I'll leave you with Matthias. He'll kind of end it with the. I guess we should end the recording at some point. But anyway, but thanks a lot,
Yeah,
Sandipan, and
no, you're welcome. Like, yeah.
I have to go. Thank you.
Okay. Do
Any
you have
other-
more questions? Or- I don't see any. Yeah, I've stopped recording.